So we're going to take a quick run through AI. I'm going to give a broader definition of it. So this is like a one-on-one, but we're gonna rapidly go through it, and it's going to be a narrative through my own product journey through AI. We'll start off. We'll show a classifier AI demo, and then we'll talk about the stuff we've been talking about already. Generative AI. What is the problem with it? And then I want to rush to what are the avenues of research that are the research in the areas of fundamental AI, new types of neural network, new types of computational elements for AI. Okay, so the broader definition mentions nothing about modeling. It mentions nothing about deep neural networks. It basically says a system that can perform a task that would normally require human intelligence. And that's a more expansive definition. And so it includes human visual perception, it includes speech, decision making, as Kwaai was mentioning, and translation between languages. So my own personal journey started off in digital graphics, image retouch, and so on, click. Would you believe that I was also out in a field, couldn't get a Nobel Prize. I was outstanding in my field. Worked for a company, Pioneer Hybrid, and that was one of the first AI projects where we used genetic algorithms. That was the fashion before deep neural networks. They thought that using the techniques of evolution, you could have a set of algorithms and you'd allow them to cross-pollinate and generate a new population of algorithms. You'd allow them you'd test them with a fitness function, and those that were fit would be allowed to propagate in the next generation. And so generation by generation, you end up with a better algorithm. It didn't work. It didn't work. What happened was the algorithms, the searching mechanism for finding the better algorithm would end up in a local valley and think that, okay, I've reached the best solution. But no, just over the next hill there's actually a deeper valley, and that is the sort of fundamental problem that it couldn't get over. My AI journey went through music gaming, the company Zaya that sold to Google. Actually, it was the second company that sold to Google. It was a startup, but it was a generative AI startup. It was a thin prompt. The prompt was you hummed a tune, and then what came back to you was a fully orchestrated pop song. And it was done in a sort of gamified way. The Unity 3D engine was brand new, and cloud computing was brand new. But hey, we wielded all of those technologies, plus this thing that was generative AI before the term was coined. My path went through face analytics. At Real Networks, we launched a face analytics division called Safer, and a natural language processing division called Context. But there was something else that I think Mike mentioned it. Somebody else mentioned it, that that human evolution, we're going to evolve to be some sort of symbiotic combination of AI and tissue. So two other jobs in my journey. One was working for the local company here, Advanced Bionics, making cochlear implants, designed the logic inside one of the generations of cochlear implants. And then that research and development we took to the sister company called Second Sight, where we developed the software behind the bionic eye. So all of this takes me along the journey to where we are now, and to think about where we take AI next. So let me talk about the two classes of AI. Most of my development experience has been in the area of classifier AI. A bit of generative AI with the music company, they're very different topologies. If you look at the classifier AI, that blue polygon, it has a thick input and a thin output. So as Kai mentioned, you might point your camera at an animal and lots of pixels are going in. That's the input. The output is, what animal is this? And so it might be a simple binary output. You might want to know, is this a hot dog or not a hot dog? Or is this image of a biopsy, is this benign or cancerous? So that might be a single binary output. Generative AI is very different. Thin input, a prompt, a very, very short prompt. The output is a paragraph of text. It might even be an entire essay. So have that in mind as we go to the next step. So quickly here, what is AI? AI is a way of asking questions of data. You train it with historical data, and you have historical answers, and that's the training process. Now, when you run it, you give it new data and it gives you a new answer. I want you to just keep in your mind that picture of dots. They come in layers. The input layer, you see where the yellow dots are, and then you have those green dots that come in layers. There are 3 hidden layers in this model, and then the output are those 2 red dots. We'll talk about what's going on in the dots. Each of those is a node. The current mathematics that's going on in that node is, the node's called a perceptron, and Colette knows what the math is going on inside there. We'll talk about that in a second, and why we need new mathematics, why this sort of model fails. Click. Let's see, we've got some builds. We'll go through the builds and then we'll get to the next slide. Fantastic. So here's actually an example. Here the historical data is the biopsy data, and the doctor's diagnosis that goes into the training data. The doctor says, yeah, this was cancerous, this was benign. So now the training is over. You now can use the model, you can release the model, and it can run inference. So that's like the learning, and the other one was the thinking phase. You obviously have much more complex models, and we can click through this until this slide builds. But this is one where this is a typical face analytics model. Image comes in, you can determine, okay, how old is this face that I'm looking at? First of all, is it a face that I'm looking at? What is the gender? What is the expression on the face? The direction of gaze? Can you even extract a signature from that person such that you can identify it? And then practical things. Are they wearing a mask? And then this, you can see the slide came from the era of COVID. Where is the canthus, the inner eye? And you can focus on it. And if you're able to read infrared, if you can read the temperature, you can scan for fever. So this was a very practical model. I'm going to demo you some of that. There we go. Hey, I'm a youngster. Okay. And so what is that saying? It's saying male. It's giving my age. It's being very generous.
Not giving your age.
And then I smiled, and it figured that I was smiling, and it knows that that's me because it's matching me against a database of faces.
Oh, it hurts.
I'm going to be a bit rude, and I'm going to point it at somebody else that it knows. What's it saying?
Pretty close on age.
Yeah.
And is it identifying you?
Mm-hmm.
Wow. Okay, because it's trained, but I don't think it knows who you are, Becky.
That is not the right age.
But you'll take it.
You'll take it. Okay, so there we are. Now look at this. This is running. This is a monster model. We'll talk about it, but we've miniaturized it. We've miniaturized it so that it can run on very little hardware. Okay, so I'm going to pause there. We can switch back to the presentation. Thank you so much.
That's all running locally on your phone?
Thank you. A lot of it's running locally on the phone. There's a lot also. There's a service up in the cloud. But that phone was running over LTE. So it it needed a very thin connection to the cloud. So that shows what's possible with classifier AI. Generative AI is a whole different kettle of fish, but we're going to talk about, so here we know about generative AI, the definition, and we've seen different examples. The prompt could be text-based, it could be image-based. In the case of that music gaming system, that was actually MIDI going up, that was translated locally, and then out came all of this. Next slide, please. So here's where we are in terms of Moore's law and in terms of the level of complexity of AI. So that face analytics stack and the work that we did at Real Networks, also in natural language processing, there were two data science teams that I created. And this is the Moore's law path of the classifier model. And this model, actually the model that I showed you is somewhere further on down. The one that's in production is this one. The one that's in production and running in a tiny processor. So that application is actually running on doors. You can go up to the door and the door recognizes you and unlocks. So now your face is your badge. And that's running locally on the device. It can run even with no cloud connection because locally you have the database of faces. So that's the power of AI over here. Generative AI is doing something completely different. Let me just hop back one slide. The red line is the path that the generative AI models have taken. And you can see GPT-4 at maybe 1 trillion parameters is very large in terms of billions, in terms of the size in which that these models take up, and the compute power, and the difficulty of running that locally on a device. However, it's not impossible. It's something we have to do. We've shown that we can take this size model and run it locally. That size model, we do have to find a way to run it locally. So let's move on. I'm going to try and rush through this. We've already gone through the Kwaai mission, but the middle one is what we're focusing on here. The importance of devoting our attention not just to tools and policy, but also look at what is the core fundamental fabric of AI, the neural networks, and the fundamental compute elements to see can we make any progress there. Because current AI is deficient, and what I showed you there where it trained in one phase and then thought in another phase, that's not how the human brain works. We learn and we think concurrently. We don't have a training element and where our brain is trained maybe in a different biological environment and then have it downloaded into our brain. No, we learn and we think concurrently. So current AI is deficient there, and if we're going to make any progress, we need to move along there. Next slide, please. Okay, so we are at Kwaai looking at a bunch of things. We want to enable models to learn and think concurrently. We want training to converge faster on much less data. There are a few proposals. One of the areas I'm looking at is called the geometric perceptron, to expand the basic matrix math of neural networks of the current thing called the perceptron, that's those circles that was in there, and use an old algebra from 1878, but it's called geometric algebra now. It used to be called Clifford algebra. So I'm not going to dive into the detail of that, but I just want to give you a taste of what's going on. And as Kai mentioned, reasoning and causation, not just correlation, is a super important part. Kai and I spent some time in Vegas. What happens in Vegas normally stays in Vegas, but the conversations you and I had, Kai, we spent a couple of days there, the conversations you had actually didn't stay in Vegas. They came back and they haunted my dreams. And you set my mind going about the pursuit that you're on, looking for causal neural networks, and my other pursuit in fundamental physics. And I found that there's actually a convergence between the two. And that's in looking at the neural fabric and modeling it as a fluid rather than an electrical connection between the different nodes. And if we model it as a fluid, we end up with a neural network that actually has causation as a fundamental component of it. And I'm not going to go into the details there. I'll give you a taster of it in a subsequent slide. What's exciting to potential investors or potential, no, they're not investors, corporate enterprise contributors that may want to sponsor research is the promise or the hope of finding a new compute element that can compute neural networks, something other than GPUs, which the industry seems to be heavily addicted to. Next slide, please. We are running low on time. I'm going to rush through this. The current perceptron was invented in 1943, and we're still using it. 1943. It attempts to mimic the human brain, the neurons in the brain, but it's a poor facsimile of it. And but it can be implemented well in GPUs. So the impetus to move off of that is low. Next slide, please. These perceptrons are stitched together so imagine each of these blue things is a perceptron. They're stitched together to make our current neural networks. But as we said, they have many deficiencies, as we've mentioned over here. Next slide, please. So the two avenues of research, geometric algebra is one. Geometric algebra is the algebra invented by Clifford. It describes a better way of multiplying two vectors. What the perceptron's doing is, and Colette can tell you, it's only computing that first term there, the dot product between two vectors. And what is missing is this second term here. Some people call it the wedge product. Some people call it the exterior product. In 3 dimensions, that would be the cross product. In layman's terms, the first term is a measure of the similarity or the alignment of two vectors. The second term is the measure of the misalignment of two vectors. It's my hunch, it's my hypothesis that this is the missing part of neural networks that gives you a negative feedback. It's like, trying to park a car and being told you're good, you're good, you're good, you're good, you're good, crash. Oh, what happened there? Yeah, you weren't good right to the end. Now where you went wrong, you went wrong in this step, this step, this step, this step. That's how training is going on now, rather than at each step being told, oh, you are 1.7 meters away from the target. Okay, you're closing in. So there's no negative feedback at each step in the neural network. And I think that's an important element. That's what we get from looking at geometric algebra. Okay, let's move on to the next slide. Causation, not correlation. That was what Kai said. Causation, not correlation. But if we treat each of those nodes as an elemental volume in a fluid, and instead of just having an electrical connection between the two, the connection is based on fluid dynamics. Now, many of you are saying, oh my God, how can you do fluid dynamics? The Navier-Stokes equations are notoriously the most complex equations. No, you'd actually constrain it quite heavily. And maybe we go on to the next slide. And here's my math for constraining it. I'm not going to bore you with it. I can already see some closed eyes. My modeling is in the next slide, and we can click to that. Right. Okay. So the modeling, I use a single element of the input node, and it is of a volume of fluid that is rotating. And just by viscosity, that's the coupling between the adjacent layers. And we can see that a spinning volume, spinning at 3, it's actually spinning at pi, it propagates its velocity field. The velocity field propagates through the fluid at, and it does it at a constant speed, a speed. It does it at where that fluid can only contact the adjacent elements. We're seeing something curious here. It decays horizontally and it decays vertically, but there's a very curious buildup over here in the corners. Next click, please. And that buildup is inexorable. And next click, please. Until, and I think there's one more, until the fluid tears. And it tears, and so hold on, what has this got to do with AI? Well, okay, so the point at which the fluid tears is the breakdown in causality, because all the time there you had a relationship between one node in the neural network and another, and you could work your way backwards. Once a tear occurs, you lose that causal path and you can't go backwards. The problem with existing neural networks is you actually can't really go backwards because there are, at each of these perceptrons, there's this activation function which is not reversible, so you can't look backwards on it. Okay, so gosh, I can see, confusion there, but I just wanted to give you a taster of where my thinking is going along. 2 paths, one on geometric algebra and one on using a fluidic fabric for next generation neural networks. Thank you very much. Last slide is just a call. Oh, the maximum speed of causality is c. As in physics, yes.
Until now.
Okay, yes, okay. So could it help us build a better reasoning AI? I think so. Next slide. Call to action. If that provoked anyone online or anyone here that's interested in computing this model, I would be super happy in getting your participation. Okay, thank you very much.